Hey everybody, this is Larry. This is day 24 of the Leetcode Daily February Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Today I slept like a lot. I don't know how, actually, I think I just kept sleeping. I woke up and I just kept sleeping. I woke up at 8 and I slept more. Oh man, 10 hours. This is the most I've slept in, let's see, since November. So that's actually pretty nice. Don't really sleep that much these days for whatever reason. So at least I'm getting giving my body finally a good rest. And hopefully recovering well for my feet. And anyway, today I'm a little bit. I have another package from probably Leetcode. If not, then then I'm just showing you a random package I got in the mail. But yeah, it's from China, so I don't know. So I have the package here. I'm not gonna, we'll open it together. Yeah, another unpacking, unwearing, or whatever. Okay, well, it definitely is a Leetcode thing because there is a Leetcode sticker. Is it on screen? So that's kind of nice. I mean, I have like a bunch of these by now, so it's nice. Okay, what is this? This thing. I don't know what it is. I guess it's just a t-shirt. A lot of t-shirts, but that's it. Wow, this is actually a polo shirt. A large polo shirt. Yeah. So now it's, can you see it? It just looks like a regular polo shirt, but with a Leetcode thing on it. I don't know. Huh. I guess this is different than a t-shirt because I think, oh yeah, that's right. They emailed me and I just thought it was regular spam, honestly. At some point, saying that I won the December Leetcode drawing or something. I did December or January because it's February now. I don't know. And I guess I just got it. But I guess everything with shipping has been very slow coming from China due to all the craziness going on in the US right now. But yeah, okay. I mean, I don't know if I'm going to ever wear this, but it is, I don't know. Is this more wearable than a t-shirt? I don't know. Just like a polo shirt. Look at me. I am, trying to be fancy while wearing a Leetcode polo shirt. Okay, I don't know. Anyway, let me know in the comments what you think. Alright, let's take a look at today's problem. We have 2467, most profitable path in a tree. There is an undirected tree with n nodes labeled from 0 to n minus 1, rooted at node 0. You're given a 2D integer array edges of length n minus 1 where edge sub I is equal to a sub I, b sub I, indicating that there is an edge between a sub I and b sub I in the tree. Okay, so we're just given a tree, we have these nodes, okay, and every node there's a gate. Okay, given amount sub I, okay, the price to open the gate if it's negative, or the cash reward on opening the gate if it is positive, I suppose. Man, this is confusing. Okay, I mean, not confusing, but I get easily confused these days, as you know. Okay, Alice is at 0, Bob is at Bob. Okay, every second they move to an adjacent node. Alice moves towards some leaf node while Bob moves toward node 0. Okay, it's very confusing. But okay, for every node along the path, Alice and Bob has to either spend money or accept the reward. Note that the gate is already open, no price will be required, okay. Nor will there be any cash reward, okay. If Alice Bob would okay. So basically we don't, so Alice has to go anywhere, has to move towards some leaf node. What does that even mean? I mean, I guess it just means that you can't, I mean, every move is towards some leaf node. That's what I mean, right? Like, it does have to be the same leaf node. I mean, if Alice reaches the leaf node, Alice is done. I suppose that's it. But every move is going to be towards some leaf node. So I don't know what that means quite yet. Okay, so if they reach the node simultaneously, they share the price or reward. Okay, okay. I mean, I think there are at least, I mean, the one part that I do understand from this problem, despite all the wording and reading and all these things, is that yeah, I mean, it's that Bob has a very clear objective, right? Bob wants to go to every node, or not, sorry, not every node. Bob wants to go from Bob's node to 0, and in the shortest way possible, because they only have one go. And yeah, and from that, you could say there's a breadth first search, right? And then Alice wants to maximize the income, right? Wait, is the... Oh, the gate is on the node, not the... That doesn't... okay, fine. To me, it feels more intuitive that the gates are on the edge, so that's why I looked at this example. I was a little bit confused, but that's fine. So then Alice starts at 0. Where is Alice? Oh, this 0. 0, and what do the colors mean? Okay, 0, 3, they open the gates, okay. They go to 1, okay. 3, 4, okay. Yeah. I'm trying to think. I mean, the Bob part I think is obvious. I always said it. And you could do that with a shortest path thing, right? And then you could break apart. And N is pretty big. And you could break apart. Each node who reaches it first. That's easy to do, right? If we do a shortest path from Alice, but then the idea is that yeah, the idea is still... Well, I mean, I think one thing to realize is also that this is a tree, right? And what that means is that there's no delaying, right? If you're going to some node, if you're going to one path, right? And I'm going to take the interpretation that when you move to a leaf node or toward a leaf node, you don't change that leaf node every time. Otherwise, you can go back and forth and kind of delay the timing, which can be possible, but it is very awkward if it's true, right? So then now we maybe have to work... What I'm thinking is that we construct the shortest path thing from Bob, and then Alice also construct the shortest thing, and then just work backwards from the leaf nodes to kind of like figuring out the max income. But man, this is I mean, it's not a tough medium, but it's a really it's a medium with a lot of involvement, I suppose. So yeah, so let's do that, and then we'll see if my interpretation is right. Right, so here we have, let's start with the adjacency list. That's basically what I always do for edges, right? UV and edges, adjacency, this, u.append we. I mean, it would be better if I typed it in correctly, right? And then, yeah, and then Bob, we can just calculate the shortest path for each node, right? So yeah, how do I want to write it? Because the reason why I'm thinking a little bit is just that I know that I'm going to reuse this more than once. Do I want to, or like reuse the idea more than once, right? And why I say it like that is because it's unclear to me how much of it is reusable and how to build it in a way such that it's reusable. So that's why I'm thinking a little bit. But I think that's not so bad actually. But yeah, we have S, so technically you could just say get shortest or something like that, right? And then you just, from a start node, Q is equal to collection.deck. We want two things. One is the distance, right? So maybe we call it none times n, right? And of course, n is going to be the length of edges plus 1, right? Because it's a tree. Okay, so then now, yeah, and then q.append start. Best of start is equal to 0, and then we just do right, q.pop left. This is the current node, right? And then for v in adjacency list of now, if best of v is none, then best of v is equal to best of now plus 1, and we want to queue it, right? Basic breadth first search stuff. I think one thing that I didn't do here, actually, I was thinking about it, but I forgot, is we want to be able to go up the tree. Maybe it's important, maybe it's not. I'm not quite sure, but that's how I want to think about it. Yeah, right? Because that's for the Alice part of going back from the leaf nodes that we were talking about. Right, so then here we go previous of v is equal to now, and keep in mind that this is a tree, so there's a unique path from every node to every other node, right? Unique symbol path if you want to be really precise. So yeah, so then this is done. We could return those two things, right? And then now Bob graph is equal to just BFS from Bob, right? Okay, and then now we could say Alice graph is Alice from BFS from 0, right? So now we have these two graphs, right? That means that we have, yeah, okay. How do we want to do it now, right? So every leaf node, what is a leaf node? Leaf node is, maybe I had to define it, I don't know. I mean, leaf node is going to be, I assume you don't start at a leaf node. What if 0 is a leaf node? I don't know what leaf nodes mean in this problem. I guess they do start at technically a leaf node, but it's a little bit awkward phrasing. But in any case, yeah, it's just going to be one where you cannot keep going, right? So then maybe we can just add a leaf situation, right? So here, I don't know. Right? So then now if it has one path out, then it's not a leaf, right? And again, these are all based on unique things, right? So maybe we have like a count is equal to 0. And then we increment, right? And then if count is equal to 0, then leaf of now is equal to true, something like that. I guess we should start at false. I wasn't sure which way I wanted to go, but yeah. And then of course we have to return it as well, right? Okay, so then now yeah, we just go through a graph, right? So okay, so how do I want to write that? A graph of 2, which is the leaf nodes. Yeah, okay, so then maybe like for I in range of n, right? So if a graph of 2, and maybe I want to use a name tuple. I forget how to quite use it though, honestly. So bear with me. So we have 3 things. We have the distance, we have the previous, and we have the leaf, right? Maybe, right? So then here maybe a graph is equal to this. I think I'm messing something up. I don't remember the exact syntax, so bear with me, right? So then now we can just do graph this, right? In theory, let's return it real quick. Okay, looks okay maybe. So, well, at least it's not complaining. I forget what. Let's print it out actually. I forget the exact syntax for stuff like this. So actually, okay. So Larry's memory not so bad, and also that means that I probably should have been using this more often. It just basically allows us to kind of wrap it around, and more importantly, allows me to do this. If a graph.leaf of I is true, then this is a leaf node. Let's propagate. Let's check upwards, right? And the thing that here is that we also have to be careful, because for a tree of n nodes, there could be n over 2 leaves, right? You can, or something like this, or -1 maybe. But you can imagine like just a full tree, and then you have n n over 2 leaf nodes, and if you kind of naively propagate every time, that's gonna be n over 2. I guess that's only n over 2 times log n, because that's the depth in that case. But you could probably get the math in a way such that it is very expensive. And at the very least, even if it escapes by, you there are things you can do, right, which is memorization in a way. So that's basically the way that I would think about it. And actually, I was going to write, and you can actually write this as a for loop with checks and stuff, but maybe that's not a bad idea of doing it memorized, right? So okay, let's check upwards. Okay, let's just say best, and best is equal to negative infinity in this case, right? Yeah, so then let's check upwards. Then best is equal to max. Best, I don't know. I'm just going. You can call it. I don't know. I'm just gonna call it go. Sorry, friends. You could call it something else if you like, right? But yeah. But basically, the idea here is just that for every node, we want to go to the previous node, right? So I mean, you can name it like, what is it? Get cost or something. I don't know. Maybe that's slightly better. But yeah, and then at a current node, right? And of course, we're gonna memorize. I'm not gonna go over memorization in this problem, and I don't know that I'm doing it right because I feel like this is a very involving problem. Like I said, for a medium problem, I don't know. Maybe I'm doing this in a crazy man's way, but yeah. But I'm not gonna go over memorization in this video just because this video is already 16 minutes and it's probably gonna go for another 10. But the idea is just that the costs don't change, right, when you have a node. But yeah, okay. So then if previous of node is equal to -1, then we just return 0, right? Because that means that you're at node 0. Yeah, maybe. We have to make sure that we do the math right, actually. But I think it should be 0. It's either 0 or the cost that is at 0 at amount, right? Anyway. So then otherwise, we want to look at this current node, right? And the current node, there's one question is the cost, and then the other is do we share it with Bob, right? So when does Bob get there? With Bob, B graph of B graph of best of node, if Bob gets there earlier, if Bob gets there earlier, then we don't count this one, but then we also so then we return get cost of the previous of node, right, plus 0, which is nothing because Bob already took it, right? But we could I'll just keep in the plus 0 for now. Otherwise, then else if the same thing, but we get there first, then we get the full cost, right? So same thing, and you could write this in a different way. I just wanted to kind of show you how I break it down case by case. Of course, for example, you can just take this out or something, and it'll be a little bit cleaner for sure. But I just wanted to kind of focus on the case by case part. But yeah, in this case, then now we get amount of node, right? Else then they are equal, and if they're equal, you have this. It's C over 2, but I don't. Oh, is C always even? I think I read it somewhere. Maybe I'm wrong though. Yeah, amount is even. So okay, so yeah, I just want to make sure because I just want to make sure that the rounding thing, right? So then now we turn get cost still the same. So maybe we could have them plus amount of node over 2, right? And that's it. Yeah. So actually, then and now looking at how I wrote this, because the amount then here, even if it don't have a previous thing, so maybe I don't even write this. It's just if node is equal to -1, then we just return 0. Then now that means that if the previous node is -1, we still kind of get this amount and do this math here, right? And that's it, I think. Unless yeah, okay, no best. Oh no, it's distance. I renamed it distance. Alright, whatever. Let's call it best because I didn't really do it that way. Previous. It's oh yeah. It's a graph dot previous because we have 2 graphs. Usually I don't have 2 graphs, so I'm just so used to writing that, I suppose. And as you can see, I had to copy and paste 3 times, which is no bueno. But let's focus on kind of looking at this first before we refactor, right? Actually, I'm going to refactor this right now because it does bother me. Because then now here you can say that maybe the cost is equal to 0, and then here yeah, cost is equal to 0 as we said. So The reason why is that it does make it a little bit easier to debug. So yeah, so cost is equal to amount of node, and yeah, and cost is equal to amount of do, and then plus cost, right? Same thing. I mean, it's still wrong, but still the same thing, hopefully. Okay, so let's see. The output is 6. Oh, because it gets to 4, right? Alright, I mean, I think the easy thing is also just like print out the get cost of I, right? Oh, not the easy thing, but the easy thing to kind of have more visibility. Yeah, so at node 2, the cost is 1, and node 4, the cost is 0, which is really not what we expect, right? Is the cost at 2, 1? It's going to be plus 2. They share the cost. So even this one is wrong, frankly. Did I do my if statements wrong? If Bob gets there first, no, that should be right, probably. What happened here? Oh, there we go. Huh. This part is actually a little bit surprising, frankly. Node. I see. The reason why this is wrong is because I did make a minor mistake, at least in understanding. It could be a big mistake in terms of implementation. Is that I consider all the paths because for the Bob's part I just did a BFS, right? So I did Bob going to 4, going to 2, and all these things. But Bob would never go to 4 or 2. So Bob would only go from 0 to 3, right? So we have to do another thing to kind of remove the nodes where Bob don't visit at all. And I think that's basically the idea. Okay, how do I think about this? I mean, we can just... this is very... I mean, it's not hard. It's just annoying to do as a medium. I'm kind of a little bit surprised. But okay, so basically the thing that we want to do then... and that's one of the reasons why I was like, how reusable we can make this. And that kind of got me a little bit. And I'm just trying to think whether it makes more sense for Bob to go from 0 to 3. And we don't really need a different thing for Bob, kind of. You could say that is, because the difference between 0 to 3 is just symmetric the other way around, right? So you can do that, but then now we have to remove all these things. Yeah, I mean, I'm in too deep, so it's a little bit annoying. I mean, I know how to fix this, but I don't know that this makes it, like, the code is really weird. How did I do this before? I did this before, but okay. I mean, it is what it is at this point. I think the idea is that now I just have to add another helper function, which is really annoying, of whether for this node, does Bob visit this node at all, right? I think that's the thing that I want to write. And you could do it recursively or not. I don't know. Maybe I can just because it is kind of the way that I've been writing it. Yeah, okay, fine, right? Basically, the way that I would think about it is that for every node, you could define a function where does it go past... Wait, does that even work? Oh, no. I'm dumb. I'm just being dumb. Because we want to go from 0 to... or from 3 to 0 or Bob to 0. Then we just go... yeah, we just mark all the paths that Bob can take and then set everything up, right? And what I mean by that is that I've been thinking dumb. Okay. So then now we have to kind of... okay. Zero out all the paths Bob will not take, right? And here... then now we just go from start is you go to 0, and then we go to b graph dot previous of start of maybe current is equal to 0. I don't like the name of start. Okay, so then now while this is not equal to -1, then current is equal to the previous thing, and this is just walking up the tree, right? And I guess now you could say maybe I don't know, path is equal to some set, right? So then path dot add current before we do, and then eventually current would be, oh, this would be -1. I think this is a little bit better. So then now it adds everything to the path, and then that means that for I in range of n, if b graph, if I not in path, that means that we should zero them out. We could zero them out by setting the distance to infinity or something, right? Yep, there you go. I mean, that's what I mean. Like, this feels very involving, and I don't know. I don't know if I'm doing it the right way in a way. Maybe there's a more simple solution is what I was looking for. Let's really click submit. And looks like we're good. A little bit on the slower side. I mean, at the end of the day, this is 2 BFS, so this is going to be linear time, linear space, right? This is the BFS. We want it twice. There are two things that you may be a little bit confused about. Well, surely I was. One is kind of this thing, but this just goes, well, this part is obviously linear, it's just a linear loop. This is also linear because it just goes up, it just path reconstruction and keeping track of what we care about. And then here, we just do a get cost, but remember that we do memorize it. So for every node, and there's only n nodes, we do all of one things. So this is only linear time. So yeah, so amortized constant, amortized constant, linear in total time, and that's it, right? Yeah. So linear time, linear space. I'm curious what I did last time, though. I feel like, did I do as crazy time as? I mean, this looks way more straightforward. I mean, is it cleaner with depth first search? Maybe. I don't know. I mean, I guess it is more straightforward in the sense that we wrote. Oh, I mean, I guess I did the same thing last time, except that I just wrote depth first search, which is basically the same thing. We calculate Bob's first, and then we do the thing where we zero out the path. Or it's just that I changed the amount instead of adding it to a thing, which I guess is the same thing actually. And we can kind of do that again. And then we run a second depth first search on the time, and that is it. Yeah, and you don't even need, like I said, you don't actually even need the second shortest path, the second BFS. I kind of just did it because I don't know. Because you can actually, if you do it from the first graph, 0 to Bob, you can just zero out the path from 0 to Bob, and that'll be the same thing. Actually, you know what? Let's actually do that. Let's optimize this because I'm a little bit annoyed at how this kind of turned out. I mean, I thought that maybe there's a easier way, but it's still going to be that, right? So here we got rid of this, right? Right. We want to here, then now we set from Bob, and then this is the path, so we basically do the same thing, right? So this is just graph, and then we don't, well, here the same idea is going to be, if it's not the path, or maybe if it is in the path, then it is the path that Bob will take, and maybe we can just remove amount, right? And then remove if, so that means that, okay, the time that it takes to get to Bob is going to be graph of best of Bob minus I minus graph dot best of I. So then you have this as one side of the cost. That's the side going from node I to Bob. And then the other side, of course, is a graph of best of I. So that means that if we get here first, right? So okay, so maybe we can write it out as a variable, right? So Alice time is going to be this thing, right? To get to I, right? Bob time to get to this node is going to be this thing, right? And then if a time is we get there first, then that's good. We don't do anything actually, right, to a map. Otherwise, if Bob gets there first, then amount sub I goes to 0. Else, if we get there both at the same time, then we just divide it by 2, right? And then yeah, and then we can just keep the cost of this graph. We don't even need this anymore because it's always, we already did the math, so it's going to actually be just amount of node, right? And we still want to memorize, I suppose, though. I mean, this is just a very easy, like almost like a prefix sum array kind of thing, except for it's on a tree, right? So I think this is mostly right, maybe not, because I just probably didn't rename everything. Because oops, this is a graph, right? Yeah, looks okay. Let's give it a submit. The key thing is that we and this is a little bit faster because we do 1 breadth first search instead of 2 breadth first search. Again, we probably can write this in a cleaner way that doesn't use recursion and function head, because there is some overhead there, but not a big. I mean, I'm not worried about it today. But yeah, I just want to clean this up a little bit. Maybe I could clean this up too, but we could keep on cleaning things up. We can do that anyway. Yeah, for now, that is all I have for today. Let me know what you think. Thanks for watching. Let me know what you think about this polo shirt. And yeah, stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.